to probabilistically model it. Okay, so let's start. So this is consultation on representation and computation. Okay, I'll say a little bit more about computation, especially about Galerkin-like computation. Yeah, because we've seen now mainly collocation and projection and regression. Okay, we've seen that they were all very similar, but they don't take care of the equation. Okay, and we're going to look now at a few other methods which do take care of the equation. Good, let's go ahead. So that's an overview of what we're going to see. So the first 4 points all have to do with parameterization. Okay, and I'll point out why this is important to do. Okay, and then we'll talk a bit more about computational techniques. This is something which did not fit in on the first day. It would have been too much. So I'll tell you a little bit about this now here too. So these two things have not much to do with each other, but they fit nicely in one lecture here. Okay, good. And there's more computational techniques which are used, but I can only tell you a few. Okay. Good. Let's start here. So with the motivation is the following. Why we're talking about representation of parameters, and why have I been using always the log of kappa in my example, for instance? That's the question. I've mentioned it already. Why? Because kappa has to be positive and log of kappa has no boundaries, no constraints, and that's the main thing. Okay, so the choice of the representation of parameters is very important. It's part of the modeling process which you do, the modeling part which you do for modeling for updating. Okay, so you do the modeling of the physics and it gives you a mathematical model, and then there's some parameters in there which may come from tradition, there's something like that and whatever. They are typically not good. Okay, so you have to model your parameters. You have to look at them, what kind of parameters I want them, and how do we want them to be able to do these updating. Okay, so the methods we've seen, both the approximation methods and the updating methods, they use ideas from linear spaces. They use subspaces. They use linear combination, arithmetic averages. They use interpolation. You only need a affine space for that, but still, you know, that underlying is a vector space. Okay, and every time you're not in that situation, it becomes more difficult. Okay, and this is true no matter whether you do the updating, sorry, with Markov chain Monte Carlo or with any of the filters. Okay, it always applies like this. And then the parameterization, we talked about this at length, should be in independent variables. Yeah. And the parameterization, of course, should respect constraints. For instance, some parameter has to be positive, like we had with this kappa. So there you saw already how to do it. I model the log of kappa, the Q. Okay. And then in the computation, I take the exponential of Q, and that goes into the model. Okay. But the thing which is modeled as a PCE and whatever, which is updated, is the Q. Okay, the other thing is just to put it into the right place in the computation. So this is respecting constraints and symmetries and whatever. And this can be actually used also in model reduction, which can exploit these structural properties. Okay, and the computational techniques, they can respect and exploit these structural properties, and we'll see how this happens. Good. So we have a model like this, and Q are these parameters, and the parameters can be very different from a geometrical structural perspective. Okay, and the original parameters, I said this already in the original problem description, as it's given traditionally, whatever, they are often not good computationally. Okay, so it is worthwhile to look at all of them and to put them in a nice format, which is good for this business of uncertainty quantification and updating. Okay. And we've already looked at this parametric kind of parametric objects in a very general setting. And what happened there was that we put new coordinates on the set of parameters. Okay, remember this was the third lecture, I think. And the principle is you can take an arbitrary set of parameters and you make a linear space out of it by taking linear spaces of real valued functions on the set. Okay, and they're not just a linear real valued function, not just a linear space, they're actually an algebra. So they have a lot of structure on something which has maybe no structure at all, the set of parameters. Okay, good. And something similar we're going to do today here also. Okay, And but we're going to talk about these parameters specifically what they are. This was a very general method on how to do it when you don't know anything about the parameters. Here we say, look at the parameters and see what they are and try to make it right away that this works well, okay? Good. And so the methods we've looked at, they work best in unconstrained linear spaces. And then we use linear methods of approximation or whatever. So this is what we want to keep doing, and that's why we have to put it into a framework that this works. Good. So what we're going to do is we're going to do probability transformations. And we've been doing this the whole time, see, because let's say our parameters Q have to have a certain probability distribution, and we transform independent Gaussians, the white noise variables. Yeah, we transform them by PCE, for instance, or any other way. I said this is only one example. It's the classical example. That's the only one I'm showing here. But many other things are possible too. So you could use neural networks or whatever to do this. Okay, but we have an expansion in white noise. That's the important thing. Yeah, why would we want white noise variables? Because they're independent. We can easily do integrations with respect to the thetas. That's what we want. Okay, so we already seen this. Okay. But now, if this is the parameter, this is again is a linear combination of these things, and it's difficult to observe constraints here. So this linear combination. So what does it do? It changes the probability law from the Gaussian, joint Gaussian of these thetas, to the push-forward measure here. Okay, but the way this is formulated, it makes it difficult to satisfy constraints on Q. For instance, if I want Q to be positive, it's very difficult to say how the coefficient should be that this is positive for all theta, okay? And that's why I modeled the log of Q, okay? And you will see this is a special case of a general idea, is I model an intermediate random variable, zeta here, okay, as chi of theta. So this could be the chi, could be a PCE like this here, okay? So that this has the nice, so this has a Gaussian law, the thetas, this has some other law, some other distribution, okay? And then I further transform it to the actual parameters in the model, so calling this Q. So in our case, I call the Q the zeta, okay, and the Q, what's called Q here, would be the kappa, and this would be, for instance, the exponential, okay? And then we satisfy the constraints as being positive, okay? So the idea is to do two transformations. One, which gives this guy the zeta, the probability distribution you want, and that's what's being updated by changing the key. It would be changing, and updating would change these coefficients here, for instance. Okay, and then in the actual computation, we have to transform it further with a transformation which may make sure how to satisfy these constraints. Okay, so finally the Q is the product of also the one after the other. First the chi, and then the upsilon here, okay? This little guy here is a upsilon. It's not a V, it's a Greek letter upsilon. Okay, good. And so I'll mainly talk about this transformation, what it looks like for different kind of parameters. Good, so here I have a list of some of the different kinds of parameters, what they could be, okay? Well, this is the ones we talk, there's many other ones, and this is something which is extensively looked at in descriptive statistics, so there you can look for more. So I'll just make short remarks about this. So first I will talk about discrete parameters, cardinal or ordinal parameters. I'll explain in a second what this means. Okay, then we'll look at continuous parameters which are bounded, for instance, or they have to be positive, that's one-sided bounded, okay? And then we'll look at vectors, okay? Vectors, free vectors, and unit vectors, and we look then at things which are matrices or positive definite tensors and things like this. So orthogonal matrices give an orientation, for instance. Positive tensors, definite, they appear everywhere in material theory. For instance, the elasticity tensor is one of these guys here. Or the conductivity tensor in our little model problem, okay? So the kappa, we modeled it always as a scalar, but really it would be a little positive definite tensor at each point in the field. Okay. So, and we want real valued fields. So we're going to talk about this, real valued fields with certain symmetries, okay, describing correlation functions and marginal distributions. So these are the kind of parameters. I will be talking about this tomorrow, more basically, how we do this here. So how the correlation has certain spatial symmetries of the field, okay. we'll talk about, so there's different, we talk about one point in the field, what the correlation of these vectors and tensors is, okay? And so these are real valued fields. We can have random fields of orthogonal matrices or random fields of positive definite tensors. Random, yeah, for instance, like for our model problem, the kappa really should be a field of positive definite connectivity tensors. Okay, good. And it's important that it respects the defining properties. For instance, that something which should be an orthogonal matrix is an orthogonal matrix. Every realization which we compute is an orthogonal matrix, as an example. Yeah? Good. Let's start with cardinal parameters. So cardinal parameters is something is just has two values. Okay. Often they're taking as 0 and 1, but already this implies a numerical ordering, whatever. That's why I took here astronomical symbols. So that's the full moon and the new moon. Okay. So these are binary parameters, a special case of cardinal parameter. So all we know cardinal parameters, these are elements of a typically discrete set. And we want to say it's this one or this one. Okay, well, here we want to say it's full moon or new moon. Okay. So, and how do we model a random variable which has to be randomly here? Okay. So there's two ways of doing it. One to model the probability distribution. It's a binary distribution called the Bernoulli distribution. Okay. Or we model a random variable which takes these. Okay. So what we do, we take a free random variable which comes out of something like this here from a PCE or something like that. So this random variable has a kind of distribution which we want for some reason, okay? But it's free, there's no bounds on it or anything like that. When it has a certain distribution function, f of zeta, okay? And we set a certain number p, okay? So we want with probability p that this happens, and probability p, 1 minus p, we want that this happens, okay? So that's how we can model a probability distribution, okay? For instance, we can take the probability of this guy happening, that's modeling a probability distribution, not regarding this p, as 1 minus f of zeta, okay? And the probability of a new moon as f of zeta, okay? Or alternatively, we can make a random variable and we say the random variable is full moon if f of zeta, so this is a function of zeta, and if f of zeta is less than p, it's full moon. So it will do exactly like this. With probability p, it's full moon, okay? And if zeta is so that f of zeta is larger than p, then we take the new moon, okay? And so this a binary parameter is a special case of these cardinal parameters. Cardinal parameters just means it's more than two values in a dictionary or something like that. So I've taken an example here. So maybe you recognize these are the astronomical signs for the first planets. So this guy, that's Mercury, that's Venus, that's Earth, that's Mars, and this is Jupiter, okay? So this has 5 members here, okay? So a real function on this one here, so this is the idea. Instead of this, we take real functions of this. A real function on this is a real random variable which can take 5 different values, okay? So it has a real value here, this one, sorry, which has 5 positions. There's a value for this one here. So we have a zeta labeled with Mercury, zeta labeled Venus, zeta labeled Earth, zeta labeled Mars, and a zeta labeled with Jupiter. Okay, and it's something in R5, a random variable with R5. So we generate 5 random variables zeta, which are free, okay, which come from a transformation from white noise. Okay, and then we can use, for instance, the softmax. I'll show you in a second what it is, to say which one we pick here, okay? So we can take the probability of, for instance, that's one way of saying, we construct a probability distribution on this here, from this. We say the probability of A is this softmax function. And what is it? That's the exponential of this one. That's something which is always positive because this was a real number, okay? And then divided by the sum over all of them. So clearly this is always a number between 0 and 1, okay? And all of them add to 1. So I can interpret them as probability. This function here is called softmax. And if you think of zeta now, for instance, multiplied by a number minus beta, then it looks very much like the Gibbs distribution in thermodynamics. This is where it comes really from. So if I multiply zeta, all the zetas by some number minus beta, it wouldn't change anything here, okay? It's just the numbers here, the values would be changing, the scale would be changing, okay? But the minus beta is typically called in thermodynamics the coldness. It's 1 over absolute temperature, okay? Okay, times kT, so this is often then the exponential of the energy. So this gives you this would be the Zustandssumme, the distribution function, okay? Good. Or we can model a random variable with the softmax. We say this random variable is A, that's one of these guys in here, okay, mercury mass or whatever, if the softmax is larger than 0.5. Because if the softmax for this guy is larger than 0.5, they all add up to 1. All the others are less than 0.5, okay? So we pick the largest one of them. That's why it's called the softmax or soft argmax. It gives you the argument of the maximum, so it gives you the largest one. There with its zeta is the largest one, okay? So that's one way of modeling discrete cardinal parameters. Now we go to the next more bit of structure. These are ordinal parameters. What do I mean ordinal? So I mean a finite or infinite set, but a countable set, okay? Now I've taken here letters of an alphabet with a total ordering. So for letters of the alphabet, we have an ordering. A comes before B, B comes before C, and so on. Okay. We don't know the difference between these two. There is no numerical scale, but we have an ordinal scale. This is less than B, B is less than C, and so on. Of course, this can be mapped isotonically. That means order preserving and bijectively, one-to-one, onto a contiguous subset of the integers, okay? So we take a contiguous subset of these integers, just as many as they're here, and then a mapping from there to here, so that the mapped A is less. So it has the advantage, instead of looking ABC, we can always look at some integers, okay? So now we want to model like with cardinal, we wanted to model the probability that it's some number K of this ordered set, okay? Of this ordered set K. So just looking at this one here, okay? Because then we have this map to carry it from here to here and backwards. So in a real computation, you may need A, B, C, D or something like that. Let's say you're doing language processing and these are words or something like that, okay? Or we'll go with the words would be more this case of the cardinal set, okay? Something which is ordered, okay? And you label this by 1, 2, 3, 4, 5, or whatever, something like that. Okay, that's the idea. Now we're going to talk a probability of 1, 2, 3. But the probability of 1 is the probability of A in this case, this example that I just made. Okay, so again, we take a random variable with real values. Okay, so we want a random values with values in K, and we take a free random variable again here with cumulative distribution function zeta. Okay, and we set then the integer m, the minimum of this K here. If K has no minimum, then this is minus infinity. Okay, it could be minus infinity. And n is the maximum of this here. If there is no maximum, then n is plus infinity. Okay. Now we set the probability of m. We take the value of the distribution function here at m. And the probability of n, the maximum, we take 1 minus the one before that, okay? And for the ones in between, we take the probability of K, the probability to be the probability that this random variable zeta is between K minus 1 and K, okay? And this is just f of K minus f of K minus 1. And then this way it was done, all the probabilities together add up to 1, okay? So now I've modeled a probability on an ordinal set of parameters, okay? Just as simply, I can take a random variable. And what will I be? If we take again a free random variable, if this free random variable is less than m, less than the minimum, then I set it to the minimum. Okay. If it's larger than maximum minus 1, I set it to the maximum. And for in between, okay, I set it equal to K if zeta is in between K minus 1 and K. Okay. So again, this random variable here has the same probabilities which are constructed here, okay, because that's the distribution function of this random variable. Okay, and by adjusting now taking this with some distribution function you want, you can change these probabilities here, make them anything you want. And zeta again would be a function of some unit Gaussian random variable, okay? So this, you give this the right probability distribution, and then you can have this discrete probabilities as you want. Good. So now let's look at the next case. These are continuous bounded parameters. Okay. And the continuous bounded ones, we take a simple now, you want a positive parameter. Well, this is something which we have. This is a very frequent case. It comes very, very often with physical models. Things have to be positive. Things having to be positive typically means that something has to be positive, definite, and this typically comes, physically speaking, from the second law of thermodynamics. Okay, is often the reason why this has to be positive. And the common solution is to set this to be the exponential of a free random variable. And you can give now to zeta any distribution you want, and then this being transformed into Q, which is then positive. Okay, and we model a free random variable as a function of Gaussians. Okay. Good. So what we model is actually the log of this variable, which should be positive. Okay, that's why I took the log of kappa. Good. And if the constraint is different for some reason, it is not larger than 0, then it's a simple shift. Okay, and if it's less than some other ones, the other bound is from the other side. Well, it's an inversion. Okay, you take minus q here, minus the exponent. Okay. In case you want, of course, this will never be 0. Yeah. Because zeta would have to be minus infinity, which will never happen for q to be 0. If you want it to, it assumes 0 with a certain probability, then you can do the following. If you know this is a positive variable, and it's always a square, so you can take the square of a free random variable. Yeah. The nice thing with this here, this is the one-to-one mapping. This one is not, but there's no way of having a one-to-one mapping like this, which satisfies this and not this, and what is one-to-one. Okay. As now a little bit more complicated, but very similar. To assume we have two real random variables, and in our models, it's always required that the one is less than the other one. Okay, or Q2 has to be larger or equal than Q1. How can we do this? Well, we can use this here to do this. We take Q1 to be a free random variable, zeta1, okay, which again is a PCE expansion of something, giving it. And then we take Q2 to be Q1 plus a positive one. Okay, this way it's always larger or equal than this one. And so this is the exponential of another free random variable. In this way, you've modeled two ordered real parameters. And of course, you can extend this to not just two, but as many as you want. Okay. And if you want parameters in a finite interval, the thing is to take, you can actually take the distribution function. Okay. Because if you have a free random variable, this distribution function goes from 0 to 1. Okay, it is a mapping from this free random variable into a finite interval, and all you have to do is now to change this interval. Sorry, it should be Q here, not C. Like this. Okay, so what is this transformation? So you scale it to the length of the interval and then shift the lower point from 0 to A. Okay, so that's what this does. Of course, you could use other functions too here, okay? For instance, the arctan or whatever, and scale this one and shift it properly or whatever. So these are all functions which map the infinite line one-to-one onto a finite interval. But as we're dealing with probabilities, actually using the cumulative distribution function is not a bad idea, okay? And for instance, often the logistics functions is taken for this one here, okay? And then it's called the logit model, or the probability function of the Gaussian is taken for that here, the cumulative distribution function. And it's called the probit model and so on. Okay. Then now let's look at vectors. Okay, these were just, if you have simple numbers now, a free random vector is best modeled by its Cartesian coordinates, okay, because they are already orthogonal. And other, we saw that the Gaussians are actually, so we model component by component with a transformation like this. Well, this will give it the right distribution, okay, but it's still completely free, okay. And now, if this random vector now has to have some stochastic properties, for instance, it has to be stochastically isotropic, as an example. That means the same probability pointing in any direction, okay? Yeah. Then the covariance matrix must be isotropic. The covariance matrix of a vector being isotropic means it has to be a multiple of the identity. Okay, so by modeling the covariance in the proper way, we can produce a random vector which has this way. And we saw in this part where we talked about linear mappings that factorizations of this here will give us here, I've written it here. So we do a factorization, okay, of a free random vector, and then take white noise times any factorization, Cholesky factorization, whatever, it will give us a random vector here with the right covariance, okay? We could have other symmetry. Imagine we want plant isotropy in 3D. So it's going to be isotropic in the x1, x2 plane, okay, and different in the x3 direction, okay. Then the covariance matrix has to look like this here, okay, if there's no covariance between the directions. So it's a multiple of the identity in the first two, and another multiple of the identity in the other one, okay. Good. So this is free random vectors. Another thing which comes up is, so one example that people often see is, for instance, a vector in R2 to model it by polar coordinates. If this is a free vector, this is not a good idea because polar coordinates are only locally orthogonal and not globally, okay. So one way would be to take R, the absolute value, and then the angle of it, okay, the arctangent of the two. But that's not good. This thing is not good. It's much better doing it this way for updating, for modeling, for everything, okay? It's different if we want to have a random unit vector, okay? Then the length is fixed to 1. That's a different matter. So this is if you want a direction, to model a direction in RD. Then we know it lies on the unit sphere, and this is a d minus 1 dimensional manifold. So we don't need d random variable, but only d minus 1, okay? Good. Of course, you could take t and d and then just normalize this always to be 1 by dividing it by that. But there's better ways of doing it, okay? And let's start with 2D. Okay, so we take, and that's actually something we know already, okay, the 2D case. And sorry, so we can think of the unit circle lying in the complex plane, okay? No, we do not have to. So one way of doing it with free random variable is the same thing here, actually. So we take this one to be the cosine of this one, okay, and the other one to be the sine. The only thing with this cosine and sine are not 1-to-1, okay. And if you want to avoid these periodicities, you can take first the arctangent of xi, which will give you a random variable between minus p half and plus p half. Then you multiply this by 2, you get a random variable between minus p and p, and then you take the cosine here and the sine. Okay, and this is now a 1-to-1 transformation onto the unit circle from a free random variable. Okay, it's sort of folding the unit circle around, folding the real line around the unit circle. And in 3D, okay, we know it lies on the sphere S2. Okay, you can take the first two components, what we did here, and times, so this is this here, times cosine of another one, which was modeled like this, and the third one is a sine here. And we've modeled a unit vector on the sphere, okay, with just 2 random variables, because it's a 2-dimensional manifold. Of course, you could take 3 and model a free random vector, and then just scale it to be length 1, okay? But there's a redundancy, you're using more random variables than you need. Good. And now comes things which have to do with matrices, and they're typically elements of a Lie group. Okay, so let me 2 simple examples which we already see now, 2 elements of a Lie group. So first of all, what is a Lie group? Okay, we've seen 2 examples of Lie groups. One is the positive reals, and the other one's the unit circle. Okay. So a Lie group in general is a differentiable manifold with a smooth group operation. So the group operation has to be a smooth operation, okay? And the operations on the group, turns out, then can be performed in the tangent space of the group. So because it's a differentiable manifold, it has a tangent space at every point, okay? But because it's also a group, the tangent space at the group unit is very special, okay? So the group unit I've here denoted by E, and the tangent space at the group unit is this guy here. That's called the Lie algebra of this group, okay? So it's a linear space. And it's actually not just a linear space, it's an algebra, but we don't need the Lie product here in this case here, okay? And it can be mapped into the group with what's called the exponential mapping, and often this is really the exponential, okay? So the two ones we know is the positive reals, because that's a multiplicative group, and the multiplication, this is a group. And the Lie algebra is just all the reals at the unit E, okay? And of course, it carries multiplication into sums in the Lie algebra, or the other way around. A sum in the Lie algebra is carried into multiplication in the group, okay? And that's why we model the log of this guy. So the sum of the logs is the product of the things here, okay? So this is the group operation, and this is the plus in the Lie algebra in R, okay? And the tangent piece, the Lie algebra, is free, okay? And mapped with exponential, all the constraints are satisfied. Yeah, because after I map it, it's in the Lie group. Okay, I'm taking the exponential of a free random variable, I get a positive one. The other one we've seen is just in the slide before is the unit circle. So now I view the unit circle as lying in the complex plane. Okay, and then of course is the group operation is just a multiplication with two complex numbers with length 1. Well, because the product has also length 1 then. Okay. And this is a Lie algebra, a Lie group we see. And the Lie algebra is again the reals at the unit E. And the E is 1, of course, the unit is 1. Okay. So you can think of the vertical tangent to the circle at the point 1 in the complex plane. And of course, the group multiplication of two complex numbers, they can be written like this if they are on the unit circle. And this is exactly the variable which is in the Lie algebra, the zeta, sorry. Okay, so the zeta is in the Lie algebra, and the plus in the Lie algebra is mapped onto the unit circle. Okay, and of course, we know this is just a short way of writing cosine and sine. Okay, good. And if we want, this is, of course, this map is periodic. If we want a non-periodic map, we have to do the trick, which I just showed before, but then it's not the Lie algebra, Lie group mapping the exponential map anymore. Okay. Good. So now we look at something more complicated, a 3D manifold. We look at SO3. These are the special orthogonal matrices, okay? So these are matrices which give not just give an orientation in 3D, you could say. So matrices, orthogonal matrices with determinant 1, okay? Now, this is a very classical thing. It's known what is the Lie algebra. The Lie algebra is written little SO3 in these fractura way of writing. These are the skew symmetric matrices. So it's a linear space of skew symmetric matrices, matrices which satisfy this here. If you transpose them, you get the negative, okay? And if they are real matrices, it means on the diagonal, because the diagonal stays under transposition, it can be only zeros, right? Because it has to be the negative itself. So a 3 by 3 matrix has only 3 different entries. It looks like this here, okay? People who've dealt with rotations know this looks like an infinitesimal rotation. This is exactly what it is, yeah? Because it's the tangent space is somehow the derivative of these matrices Q, okay? And it's well known, if you take the exponential of this, the real matrix exponential, well, you get an orthogonal matrix. So this would be the mapping, this epsilon of zeta with a Q here. Okay, sorry. I would have called this zeta. This is wrong name here. And so what we model is this here, and then we take the exponential of this. So we model the log of this here, and then we take the exponential of that, but we take only these 3 numbers, and we have an orthogonal matrix. So this is strictly orthogonal here, what comes out here. By the way, it's not an infinite series, it's a finite sum. So look it up. It's called Rodriguez formula to compute this here. So it's very well known. So that's the best way to model this with 3 random variables. What is an awful way of doing it is if you take, for instance, the Euler angles. That's a terrible way of modeling here for our purposes. Okay, it's not a good way. So Euler angles are out, and this here Rodriguez formula is in, so to speak. Okay. Now, if we have additional symmetries, like for instance, this has to be in a symmetry group, a smaller one than SO3. Okay. Well, then this can be composed on S here. Okay, these conditions. Because the exponential will keep those conditions. If they are linear conditions, they're typically linear conditions in S here. Some subspace of S. Good. Another important case is positive definite tensors. One of the most important cases, actually, when you model physical things. Okay. The thing is to see that every even tensor, which you can regard as positive, they can be also seen as a linear mesh. So positive definite tensors have always even order. Okay, so I'll take an example, one of a sixth order tensor here, and that can be viewed as a linear mapping on the space of third order tensors. Okay, because I just do the contraction about this and this indices. So this is the Einstein summation notation. I just add over ijk. Yeah? Take the product here with ijk and add over them. Okay, and that's the result. So that has these indices element. So this is a symbolic way of writing this tensor product. Okay, contraction, by the way, it's a contraction of the tensor product. We see that's a linear map. Okay, it's linear in the V. Okay, so that means I can represent this as a matrix, this tensor, and it's very well known. It's called the fourth representation to represent, for instance, the elasticity tensor as a matrix. Elasticity tensor is a fourth order tensor, but it's often represented as a matrix. This is you do by choosing a basis for the tensors here. Okay, so now, and it's symmetric positive definite exactly when this matrix is so. Okay, so we're going to look now at positive definite matrices. Yeah, and then you can, via this correspondence, you can go back to the tensor. Okay, the positive definite matrices, they're necessarily symmetric. We write like this here. So symmetric matrices, plus means they're positive, and the times here means they're positive definite. Okay, good. So geometrically, this is an open cone in the vector space of all symmetric matrices. So we know the vector space of all symmetric matrices has dimension n times n plus 1 divided by 2. Okay, and because it's an open cone, it has the same dimension here. It's also it has the dimension here because it's an open cone. Okay, so it's a Riemannian submanifold, and it's under matrix multiplication. It is not a group, unfortunately, but it is some other operations. Okay, and then you can see that the tangent space, it's not important which these operations are, but in any case, the tangent space at the identity, yeah, of course, that's a symmetric positive definite matrix, are all symmetric matrices. So you take all symmetric matrices, and that's the tangent space at the identity. Okay. And there's also an exponential map. If I take a symmetric matrix and take the matrix exponential, it's a positive definite symmetric matrix. Okay. So we know symmetric maps have this dimension. So I take m free parameters, which I can do. So, and I can model a symmetric matrix by just putting them, the first ones on the diagonal, or the other ones on the upper half, and the other one just by symmetry. Okay, so I can model subspace of symmetric matrices by a vector in Rm, where m is this here. And then I can take A of Q is just the exponential here. So, okay, so that's the mapping epsilon we were looking at. So in 2Ds, it looks like this here. Yeah. Just there's three parameters, Q1, Q2, Q3, and because it's symmetric, these two have to be equal here. Okay, and then you take the exponential. That's one kind of parameterization to do this. Okay. What this doesn't do, it doesn't take care of symmetries of A or the tensor which is behind A. Okay. You can do it because by noting that the symmetries of H are those of A. Okay. How is it to see these symmetries? So often they're important. You want a tensor which is isotropic, or a tensor which is orthotropic, or something like that, and you want your model to reflect it. So this mapping has to reflect this. So to explain this is typically to look at the spectral decomposition of these guys, at the eigendecomposition. For the symmetric matrix, we know we can write it like this, with this a diagonal matrix and orthogonals V and V transposed. Yeah? So lambda is a diagonal matrix. And then we know that A, which is the exponential, this is the way, by the way, the way to compute it if you have the spectral decomposition, is just the exponential of the diagonal matrix, which is a diagonal matrix which with the exponentials on the diagonal of these eigenvalues here. Okay, these guys here are e to the lambda now here. Good. So, and now what we can do here, which was not possible, it's hard to do with this kind of parameterization, is we can separate the orientation, the randomness of the orientation and the symmetries in which are reflected in this orthogonal matrix V from the strength. And the strength is in the eigenvalues, and model them separately, okay? So what you can do is to model the first n components. So this is the model, sorry, you model the diagonal matrix, which has length n with the first n components of this vector qm, okay? And the rest you take to model the orthogonal matrix V. But if you have symmetries, the number of distinct lambda j's is often reduced, okay? For instance, the elasticity tensor, if it's isotropic, it has only 2 different eigenvalues, only 2, not 6 that you would expect, for instance. There's only 2 different eigenvalues. And we'll come to this in a second, okay? Here, down here, okay? And the orthogonal matrix, you could model this with a skew symmetric Q, as we did for SO3 before, okay? And then take the exponential mapping. But if the background tensor of the matrix is really a spatial tensor, only spatial rotations enter, okay? So not all W's are necessary here, only ones which come from spatial rotations, okay? And it's known how to compute these V's then with this as a result of the spatial rotation, okay? And that needs only 3 parameters here, okay? So you need fewer to model that. For instance, the rule for the elastic tensor is, which is a 4th order tensor, yeah, operating on symmetric tensors, namely the strain, giving another symmetric tensor the stress. For instance, in the isotropic case, we know there's only 2 distinct eigenvalues. The bulk modulus, which has multiplicity 1, and the shear modulus, which has multiplicity 5, okay? So all you need is 2 random variables which model these 2. These 2 have to be, of course, positive because they're eigenvalues of a positive definite tensor. So what you model is the log of k and a log of g, okay? And that's a free random variable, and then you take the exponential of them to get k and g, okay? Never ever use Young's modulus and Poisson's ratio. These are horrible parameters, okay? So these are the ones to take. Good. And now I want to jump. So this is what I want to say about modeling parameters. Now is a little jump to a little bit on advanced solution methods. So we've seen regression, collocation, and things like that, spectral projection, okay? They really actually took no regard of the solution of what kind of equation it had, so especially of the governing equation, okay, and of the structure. The structure we've seen is already leads to tensor products. So this is what came out from our approximating linear mapping. So if we had a random field, there was an associated random linear mapping, okay? And this linear mapping was factorized, the singular value decomposition, and this led to tensor products, okay? And it turns out the stochastic space which comes out of there, which is one part of the tensor product, is actually it's a tensor product of further smaller spaces. And these leads to low-rank tensor approximations. That's something I'm not going to be talking about today. That's something for tomorrow, okay? But this allows us to deal with thousands of random variables, okay? Good. And this way, this reduces to numerical linear or multilinear algebra, what we have to do. We work with low-rank tensor representations, okay? That's something for tomorrow. What I want to talk about this today, and this is where this comes into, it makes it practical again, is these Galerkin methods, okay? So I'm going to talk about, just touching on it really, on non-intrusive Galerkin, in reduced basis Galerkin methods, on proper-generalized decomposition, which is a way of producing this low-rank tensor, what I was talking about with Galerkin methods in the first place. And low-rank tensor methods, actually, I'm not going to mention in Bayesian regression. I'm also not going to mention it, something for tomorrow. Okay, so that should have gone away here. Good, so let's look once more at Galerkin. We looked at very quickly. So in Galerkin, we have, this is our governing equation. So that's the residuum, actually, of the governing equation. And that has to be 0, okay? That's very difficult to do for all parameters theta. So that's why we used interpolation, collocation, whatever like that first. Now we're going to use Galerkin weighting, okay? So you make an ansatz, or just use Galerkin weighting in these variables, in this theta dependence. So we just going to use Galerkin weighting with these ansatz functions here, okay? So that's the ansatz. We have to determine these coefficients, and we use Galerkin weighting. So we take the residuum and weight it with one of these and take the inner product, okay? Remember, this is the expected value of this times this, okay? And this we require to be 0 for each of these ansatz functions here, okay? So this gives us a huge system of equations. I showed you already what it looks like. Okay. So if you write the matrix for that, it looks like this, where every dot here is a full-blown finite element matrix. So you never ever want to form this in the memory of your computer. This matrix is only to be treated implicitly. You never ever form this matrix. But this is a huge system of coupled equations, okay? And being coupled equations, and people who know a little bit about coupled systems, and then we can treat them with the methods of a coupled system, which is a partitioned methods to do this, okay? To remember is what we do when we computed regression, pseudospectral projection. We actually solve this for samples. And what we have here is this iteration equation to solve for this sample, okay? So this is the residuum, this is some preconditioner, that's the old, and this is the new iterate, okay? This looks very much like the Kalman filter if you look here, but it's something different. So it's an iteration, and I can write it like this. So this is the increment in the iteration, okay? And now the trick to get this non-intrusive, to not have such a huge system of equations, to solve it in a partition way, is to apply the weighting not to this equation, but to this one here, okay? This is a fixed point equation. Okay, let's go here. The way to do this is the following. We write this equation like this for the coefficients, which we want. Okay, that's the update of the coefficients. And now I do Galerkin weighting for this equation. And so if I do Galerkin weighting for this equation here, I get for the, so this is clear. These are the old coefficients, and these are the new in iteration. And what's the delta? I have to write down what the delta is, and the delta is this here. And so it's inner products, Galerkin inner products with the preconditioned residuum, okay? And now if I compute this here by sampling it by some quadrature method, well, then I replace this here by this here. You see, it's just sampling the preconditioned residuum. This is what I have to do. Then I have to multiply it with this and multiply with the weight, if there's a weight, and I get this term here, okay? So what you do when you do a regression or collocation, you take one sample and then you iterate to convergence. Then you take the next sample, you iterate convergence. What you do here is you take all samples at the same time and do one iteration on each sample, and then you do this update. And then you do another iteration on each sample and do this update, okay? So this is now the non-intrusive Galerkin. Okay, so what is this is actually, for people who know a little bit about coupled methods, this is a Bloch-Jacobi method on the coupled system, okay? Good. So there's a little numerical example. We have electrical network here where there is, where these guys are random here. So they're nonlinear resistors, random in this way here, okay? So this lambda of P is a nonlinearity acting on the square, on the cube actually of the resistors here, okay? Good, so these are nonlinear resistors, and they depend on one parameter here and here. This is the current which you feed into, okay? And now there's different ways of doing this, okay? And it says here, you see how this converges, okay? We set the convergence tolerance, and this is how the error goes down, the RMSE, okay? Depending on what kind of order polynomials you take in the Galerkin expansion, okay? So this goes down. This is how good you can get with second order polynomials. This is how good you can get with third order polynomials. This is how good you can get with fourth order polynomials. This is how good you can get with fifth order polynomials, okay? So you see how well the equation is satisfied with Galerkin, okay? We compared it here with projection, pseudospectral projection. This is a number of solver calls. You see this is about the same work as pseudospectral projection, but this, you get something which solves the equation in some weak sense, okay? And this can be accelerated now by using faster methods than Bloch-Jacobi and by using low-rank tensor approximation. So I'm not going to be talking about this. So this is I'm just touching on it. So the next thing I want to touch on is the reduced basis method. It's also a Galerkin method, but it uses a reduced Galerkin basis. The way to do it is to use samples as a Galerkin method. So having compute samples, K1 to capital K, actually, it has a bit more than what I'm presenting here. It has a method of how to pick a new sample, okay? A new sample which will make the error very small in a certain sense, okay? And you take now this here as a basis for a Galerkin subspace. So you take the span of these vectors, UK, okay, and you make the ansatz for U theta is this UK. Now I put them here into as columns into this matrix times this small vector. This only has length K here, okay, like this here. Okay, and these guys now, they could be expanded by a polynomial chaos if we wanted to, okay? But the main thing is now, how do I compute these coefficients, okay? These ones here are directly V of theta, and is by doing a Galerkin weighting. Either if you want to compute V of theta directly, that's often done. Whenever you want a new V theta, you solve this little system. This is only K by K, okay? And then you weight just with uj for all j. If you want these coefficients, you have to weight with these combinations. So that's a bit bigger, the system, okay? But this is a small system now to be solved. A small coupled system. Again, we can uncouple it in the way which is just presented before, okay? Good. The next one we want to talk about is PGDs. It's called proper generalized decomposition, and this is successive rank 1 updates. There's 2 names for this here. Assume my governing equation comes from minimizing a functional. Okay, so this is just the derivative of this functional being 0. Okay, then solving this is equivalent with minimizing this. Okay, and in variational form, this looks like this. This is 0 exactly when this holds. Okay, now we define, because we have random variables here, that's for one fixed theta, because we have random variables, we define a new functional, which is just the expected value of this guy here, okay? And this is something on this tensor space with inner product here. So, and now we work in this tensor space, and we want the tensor which minimizes this. This will be the solution which solves this in a Galerkin sense in the best way, okay? Okay, and the solution to minimizing this over U is to write down what the equation is. This is the variation way of writing it down, okay? And now the idea is the following. Assume we have an approximation of this guy as a tensor. Okay, so we know this is a tensor, so it's something like this. Assume we have a low rank approximation of rank R minus 1. Yeah, okay. Now I'm going to compute the next one. Okay, one more. Increase rank by 1. Okay. So I do the following. I said UR is this here. Okay, and now add a new term. So I keep this here. I computed this beforehand, and now I need to add a new term. So by minimizing, we respect with W and with eta. So I take the derivatives with W and eta, okay? So of course, this is a coupled system of equations, okay? This is the Galerkin conditions of solving this here. And so I can define this functional, just this part here, just to use this. And the derivative of this, of course, we want the derivative of this to be 0. And this is 2 equations. One, the derivative with respect to W, and the other one to respect to eta. 2 systems of equations which are coupled, okay? And now we solve them again in a Bloch-Jacobi partitioned way, okay? It's actually a Bloch-Gauss-Seidel solver, solid here, okay? You solve this first for this one, then you take the solution, put it into the other one, and just repeat this until convergence. When it's convergent, you have one more term, then you increase R until it's accurate enough, okay? So this is the PGD computation. It gives you a low rank approximation. Okay, there's an example now. Here we have this obstacle, and there's a string growing over this obstacle, okay? But we don't know where the string is attached, okay? So we have a probability here of the string being attached somewhere, and this is the proxy function. So this is the string in all different positions. It's something which was computed in this way, okay? You can see as a PGD. And there's different ways of doing it, and you can see how quickly the rank goes down to 0. That's one way where the rank does not go to 0 very quickly. And then we have another version where the rank goes to 0 just as quickly as the SVD. So you see with rank 1, we only need 10 terms, and we have an accuracy of 10 to the minus 1. So that's a Galerkin way of producing a low rank approximation here, okay? Good, so this brings me to my conclusion. Sorry, I'm going already again 7 minutes over the time. So we talked about proper modeling of constrained quantities, okay? Because we have linear approximation methods and linear identification methods. We have difficulties with nonlinear constraints. And also Markov chain Monte Carlo will have difficulties with nonlinear constraints, because you have to have a prior which satisfies the constraints. You have to have a proposal distributions which satisfies the constraints. So this is all a pain in the neck, so to speak. Okay, so you want no constraints. And that's why it's good to make these transformations. So it's possible to find transformations from free random variables to these constrained quantities, okay? So I've covered a few of them. And then we looked at Galerkin techniques, and we can see the Galerkin, which looks blowing up a huge system. We can make it non-intrusive. That means we can use our original solver. We don't have to write new software, okay? And it can be done in a simple way of just doing one iteration at a time at each sample and combining them, okay? Or we have these methods like reduced basis methods or PGD, okay? And reduced basis methods has just recently been compared with pseudospectral projection. And it turns out for the same work, reduced basis methods are more accurate, okay? So, and they satisfy, what comes out satisfies the equations in some weak sense, okay? An important thing which comes out here, we'll stress it again, which was used here, is that the solution to these parametric problems or stochastic problems can be represented in the tensor product space, okay? And that's something I'm going to pick up tomorrow again. So thank you very much for your attention. If there's any questions now, please put them now.